All right, let's talk about how to factor a quadratic expression if its leading coefficient is greater than 1. So first of all, this is a quadratic expression because it has a y squared and a y to the first power in separate terms. Because they're in separate terms, there's no way for us to just combine them and kind of be done with it. There's no convenient way to get it so that the y's are only in a single term, which turns out to be a problem if we want to solve equations involving these expressions later on. So factoring is going to be our way of getting to those solutions for now. So what's going to be our strategy? Fortunately or unfortunately, we're going to have to use a guess and check strategy here. And the way we're going to guess and check is we're going to look at factor pairs for the leading term, 3y squared, as well as for the constant term, the 16. By taking factors from factor pairs of each of those, we should be able to guess and check our way to a factorization that'll work. So we'll do that by first listing all factor pairs that we can think of for 3y squared, as well as all factor pairs we can think of for the number 16. Then we'll use those to build binomial products from each factor pair until we find one that multiplies and simplifies out to our original expression. So let's start by finding factor pairs. So how can I split 3y squared into a product of two factors? Well, there's only one way to do it because 3 is a prime number. The only way to split 3y squared into a product of two quantities is to make it 3y times y. So the fact there's only one way to do that is actually really helpful in this problem because it's going to limit the number of factor pairs that we need to include in our guessing and checking process. 16, on the other hand, has a lot more different factor pairs that we can write for it. There's technically 3 distinct factorizations for 16 into pairs: 16 times 1, 8 times 2, and 4 times 4. But for reasons that will become obvious in a moment, I also want to consider the ordering to be a little different. So I want to include 2 times 8 and 1 times 16 as a 4th and a 5th factor pair for 16. So now we've identified all the factor pairs for these two expressions. We need a prototype. What is our factorization going to look like? Well, because both the constant term and the linear term, the term with a degree of 1, have plus signs in front of them, that means I should be looking to factor this expression into a product of binomials, each of which has a plus sign in it. So the first factor will look like something plus something. The second factor is going to look like something plus something. And those somethings are going to come from the factor pairs that we identified. So for example, the 16 times 1 factor pair that we got for the number 16. If I match those factors up as the second terms of the factors in my factorization, using 3y and y as the first terms in my factorization, that's going to give me a candidate factorization of 3y plus 16 times y plus 1. I'm going to do the same thing for all the other factor pairs that we have here as well. So we have really 5 different possibilities for how this expression might be factorable. Now it's just a matter of checking to see which one of them actually works. If we're using our little table to keep track of our process of multiplying polynomials together, one way to look at it is we know what we want inside of those 2 boxes. We know that we want a 3y squared, and we know that we want a 16. And there's only one way to get 3y squared out of our product of 2 lower degree polynomials. The only way to do it is to have a 3y times a y. But the 16, there's a lot of different ways to do. And how we factor that 16 is also going to determine what gets multiplied by the 3y and the y to fill out those 2 boxes in the diagonal of this little chart. For example, if I have 16 and 1, so if I use the 3y plus 16 times the y plus 1 factorization, then those cross terms are going to be 16 times y and 3 times y, respectively, 3y times 1, if you like. And if we then combine those like terms together, we're going to get a total of 19y as our middle term. And so if I were to multiply 3y plus 16 times y plus 1 all out, we'd get 3y squared plus 19y plus 16. But that's not what we're looking for. We're looking for 3y squared plus 16y plus 16. So that means that this is not the right factorization for us. This is not the one that we want. So we'll go to the next one. If we use 8 and 2, then our cross terms are going to be respectively 8 times y and 3y times 2, or 6y. And when I combine those like terms, I'm going to get 14y as my cross term, which also doesn't match up with what we wanted. So that one's no good. So we'll try 3y plus 4 and y plus 4. That's going to give me a cross term of 4 times y and 4 times 3y. That's 4y and 12y, which when combined give me 16y. And that's the one I wanted, looking at my original question. And so we found one product that simplifies out to give me the thing that I originally wanted. There are some more sophisticated methods for factoring quadratic trinomials that have leading coefficients greater than 1, but in my own experience, I tend to rely on this one more than any other, just because it doesn't require us to do anything too sophisticated. We just have to know, how does 3y squared factor? How does 16 factor? And then try various permutations of those in our binomials until we find one version that multiplies out to the original.